This is section 3, Sounds in Strings Revisited. For this section, we're going to have exactly the same setup that you had in section 1, but rather than investigate how the pitch changed with length, we're going to look at the wavelength that's going to be generated by the string. Now, our setup is the same. This time we're starting with an initial length of 75 centimeters for the length of the string. Once again, we're going to strum or pluck the string and hear the pitch that's being generated. Now, as the string vibrates, the string is vibrating as a whole, similar to what's shown in your text on part 4 of this section. Now, when you see this, the string vibrates from one end to the other, up and down. The wavelength of the associated string, though, is actually double that length. For A, record the length of the vibrating string and the wavelength in the table in your log. And then we're going to reduce the length of the string once again to where it is now 50 centimeters. If I move the meter stick back here to this position, you'll see that it is just about 50 centimeters from the cup to the edge of the table. And that's the length of the string that will be vibrating. Strumming the string once again, you'll hear the pitch. 5A. Record how the pitch frequency of the sound changed. 5B. Record the new length of the vibrating string and the new wavelength of the standing wave for this shortened string. We're going to reduce the length of the string to 25 centimeters. And once again, plucking the string. 5A. Record how the pitch frequency of the sound changed. 5B. Record the new length of the vibrating string and the new wavelength of the standing wave for this shortened string. Seven, A, in your log, make a general statement about what happens to the wavelength as you change the length of the string. Seven, B, make a second general statement about what happens to the pitch or frequency of the sound as you change the length of the string. 8A, what wave property changed to make the frequency higher? As a hint, recall that the wave equation is V, the velocity, is equal to the frequency times the wavelength, which is given the symbol lambda. If the wavelength remains the same and the frequency changes, what else needs to change? Now for part 9 of Sounds on Strings Revisited, we're going to investigate the relationship between frequency and wavelength and wave speed. Now, we're going to do a slight variation of what your classmates did in class. Rather than putting masking tape down on the floor, we're going to use the tiles that are on the floor. Each of these tiles is 30 centimeters long. To perform the experiment, what we will do is we will then step on each tile at the beginning of the tile once every second for a distance of 2.4 meters rather than the 10 meters that you did in class. But the results you get will be essentially the same. For our timing, we're going to use the time-honored method of counting rather than have a student count off 1 second intervals. So just counting and starting at the first square. 1, 2, 3, begin. 1, 2, 3, 4, 5, 6, 7, 8. We traveled 8 squares which would be 8 times 30 centimeters, a total distance of 240 centimeters in 8 seconds. Our frequency was 1 per second, and our wavelength then was 30 centimeters. 9A. We timed the overall travel, and then you should have calculated the speed by dividing the total distance traveled by the time elapsed. Compare that result to what you find from multiplying wavelength times frequency. We're going to repeat the same experiment now, but we're going to do it once every second, but instead of stepping 30 centimeters, we will step twice 30, or 60 centimeters. Going back to the beginning again, once again starting on the wave, the first square for our wave, our frequency will still be 1 per second. So starting again, 1, 2, 3, start. 1, 2, 3, 4. This time we traveled again 8 squares. We traveled that in 4 seconds. 10A. Again, compare the speed for the trip with the result obtained by multiplying wavelength times frequency. Finally, we're going to repeat and do it with a different frequency of once every 2 seconds. Going back to our beginning. Now we're going to step on every square once again like we did before. And this time we'll do it once every 2 seconds. So again, starting like we did before. 1, 2, 3, begin. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. This time, we had a wavelength of 30 centimeters, the length of 1 square. Our frequency was 1 per every 2 seconds. The total distance we traveled was, once again, 240 centimeters, but this time we did it in a time of 16 seconds. 11. A, again, compare the speed of the trip with the result of multiplying wavelength times frequency.